glad you're here. So today we're at the end of class, but I'll wait at the end of class because the online people don't want to hear me going through a seating chart. We're going to do some administrative stuff, like the seating chart. I'll take pens again. If you've got questions about mastering biology, we'll say those to the end as well. And I also need to know who's a bio major, but again, that'll be at the end. Today's class is the first bit. We're going to go over the lab, this week's lab, and then we're going to go over the context of biology. Some of this, why chemistry is important for biology, and some of just the terms to get all up to speed with this. All right? Back to class, how's the volume? Good? Okay, so with lab, you should have access to now online, like a Word document that has this week's lab, blah, 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 blah. It's got a bunch of questions about the scientific method. And it has, you're supposed to come up with an hypothesis about why M&Ms melt, why they melt better in your mouth than in your hand. And I've got a bunch of M&Ms for you to take on your way out, so you can do this. I mean, you can buy your own M&Ms, but you know, you don't have to have your own M&Ms. You can do this. The first part of that, which I thought we'd be all in person doing, so we're going to do it here in the lab, in class instead of lab, is this puzzle, trying to figure out a rule. So the scientific method in general is trying to figure out what's the rules for the universe, right? More or less. So here's the puzzle. Stay with me. And if you've seen this before, don't blur. Thanks. But yeah. Got a series of numbers up here. Okay? Feel free to follow along, write your notes on your notebook if it helps. And this series of numbers, there's a rule I've written down in my notebook that this series needs to follow. Okay? These ones all follow so far. And it goes on for however long. Okay? What you get to do is you can ask, does this number fit next? Does this number fit next? And I'll tell you yes or no. Once you think you've got an idea of what the rule is, you can check that's the rule. I'll tell you yes or no. Okay? Any number people want to guess for fitting up here? 10? Yeah, 10 fits. Yeah? 12 fits. Anybody want to guess the numbers? Anybody want to guess a rule?
Guess a rule.
Yeah, okay, guess a rule. Loud.
+2.
+2 is her guess. That's not the rule. Anybody want to guess any more numbers? Guess different rule? Yeah.
I can't remember the name of the rule is. It's just even numbers.
Is it even numbers? It's not even numbers. Is anybody bugged yet? Feel free to keep guessing numbers if you want to. Okay, hold that thought. We're going to talk about your roommates and then we're going to come back to this, okay? So, well, it looks like it's even numbers. It looks like it's up by 2. I'll give you that. Let's say you got your roommate and for whatever reason, stay with me on this poor analogy. You're not going to just talk to them like a normal person because that would be too easy. But let's say you've seen your roommate eating a lot of vegetables, right? This roommate is great. He or she has like eaten salad and like mostly vegetables all the time you've seen them, okay? And you think the rule they're following is that they're vegetarian. You're like, I think that's the rule they're following. Cool? To test that, if you want to test that, and again, for some reason you can't ask them. If you want to test them, you show up with a rutabaga and they're like, hey, do you want to eat this rutabaga? Is that how you test this? Why not? People are shaking their heads.
Because you've already seen them eating vegetables. Why would you give them why would you offer a vegetable?
Right, okay, yeah, so and they don't have like all vegetables to still be vegetarian, right? And yeah, you've seen eating vegetables. Who cares like rutabaga? I even know I recognize a rutabaga that bit me, right? Like I'm sure it is, but okay, we'll go back. What do you show up to the? What do you ask? What do you try to check? How do you check if they're vegetarian? Bring a hamburger, right? It's entirely possible that they're not a vegetarian and don't like hamburgers, right? Some people I like that. But if they like a hamburger, you know your rule's broken, right? Are we with me there? Okay, so, cool. If we think the rule is even numbers, if we think the rule is vegetarian, and we check another even number, or we check another vegetable, a yes to that doesn't tell us anything, right? So, if we want to check if it's even numbers, what if true would disprove? So like, if your roommate eats a hamburger, that disproves they're vegetarian. What if true disproves evens? Odd. So what do we want to check? We want to see, is this an even rule? What do we check? Pick a number. 13 works there. Okay. So if 13 works, now what's a new option for what our rule could be? Say what?
Random.
Random numbers. Okay, so we think it could be any number. Okay. What's the weirdest number we can think of? Pi? Right? Okay, so should we check that? It's not. I don't like 3.1415, 6, whatever. Okay? So now we've got that idea. Okay, so it can't just be random numbers, but it's not just evens. Any other ideas of things this could be?
Whole numbers.
Whole numbers. Okay, so if we think it's whole numbers, how do we check that? The number, and then the pi helps out with that, right? So like, okay, so whole numbers, it's a really good guess, right? So far, we've got a bunch of these. So like, does it have to be increasing whole numbers? We check for a small whole number, one that's less, right? And if you guess 1 here, that would totally work, okay? If you want to be super funky, you could be like, ooh, do negative numbers work? How do you check that? If we think it has to be positive whole numbers, how do you check that?
-7.
-7 doesn't work. So now we've got a better idea of what our rule is, right? And that totally the rule. Props to you all. The rule is, for this case, positive whole numbers, okay? Now, you can't ever know, with science, this is going to be disappointing, you can't ever know something a bazillion %. You can't be completely sure, because maybe the actual rule, the universe isn't going to hold up the notebook and tell you what the rule is. The rule might be all positive whole numbers except for 47, right? And you don't know that, but you're gonna make the best guess you can, all right? And the whole point of this, I realize is tricky, and it's not. Okay, it's sort of meant to be tricky, but the obvious thing is to want it to be +2, right? And that's what people generally think. They're like, ah, this cold medicine said it'll cure my cold. I took it. I got over my cold, therefore it's great, it works beautifully, right? The scientific version of this is like, oh, most people get over their colds anyways, right? If you want to check if your cold medicine actually does what you think it does, right? It's better than just having a cold by itself. How do you test that?
Give it to one person and not the other.
Yeah. So sorry. I realize that I'm rarely going to repeat stuff back, but it's because the recording, it's easier for that.
That's
So in
okay.
case you're like, I just said it. So she said, you can give it to one or a group of people and not the other, right? Because that's like offering the hamburger, right? If there's no difference between these groups, that disproves your rule, right? You're trying to figure out something that if true disproves your rule. So if there's no difference, your rule's broken. If there is a difference, you're like, I'm liking where this is going, right? And you can try it again, well, like maybe that they got anything made them feel better about it, right? And you keep trying, but the more you try to disprove your rule, and if you still can't, then you're pretty sure you're right. Does that make sense? Are we okay with this? Okay. This is a hard concept to get for a lot of people. And then some people are like, yeah, this is how I think in general. That's good too. Questions about this? Sweet. That's the first part of your lab, and it sets up the rest. So the rule is this positive whole number situation. And you get there by trying to disprove whatever idea you think is a problem. Questions? Comments, concerns? Great. Okay. On to biology. Let me just check this because I'm paranoid. Sorry. Yeah. Okay. Biology has to play by the rules of physics and chemistry. I realize you want to be a biology because you think it's the best science. It still has to follow the rules of chemistry and physics. Stuff. So the science version of stuff is matter. I really gonna harp on this. Maths need to cover like as much of your face as possible, not like eyeballs, but noses, things. Yeah. And also, when people change masks, and this is good, you should change your mask, it's gonna throw me off and be like, do I know you? Anyways, it's gonna be good. And after the play, which you should totally refer to as after the play, because it sounds cool. A bunch of people will introduce yourselves, they'll be like, oh, hi. Anyway, that's beside the point. Okay. Matter takes up space, has mass, and gets made up of elements. Okay? Element is the substance that you can't break it down into anything else with chemical reactions. Anybody here played Legos as a kid? Yeah. Were any of you good at Legos? Like, I can make boxes. I'm like, I make a box and they're like, yep. But one of my brothers, like, he could actually, like, make things. Were you people good? Oh, nice. Congratulations. Like, I was impressed. Like, I don't know how to do anything else. Okay. So you can make cool things. You can make a beautiful box, or you can make, like spaceships and stuff. Make a bunch of stuff, but when you break it down to the individual Legos, you're at the brick level. The little brick, that's a little red brick, keeps its little red brick identity, whether it's in a spaceship, whether it's in a catapult, whatever it is in, it's still a little red brick, right? Elements are similar. They show up in lots of different ways with lots of other elements. They're stuck in different patterns, but their fundamental, what they are, that stays the same. We're okay with this? Your book talks about this a lot, and they use non-Lego terms, but that's the idea. You're going to see compounds as well. The compound is going to be two or more elements in a ratio that's together. So like those Lego wheels, right? That little yellow part and the little tire part. This is the unit that you use, right? The ratio is 1-to-1, and you'll do stuff with it. But you could break it down into its fundamental parts. You could break it down into the yellow part and the tire part. But the compound they're stuck together. They operate as a unit. Will work me there? Okay. This is where it gets tricky. Not super tricky, but a little bit tricky. Elements, the fundamental elemental identity stays the same. Always, always, always. It just does. You can't change with chemical reaction. Talk to the physicists with nuclear reactions if you want to get beyond that. But for biology, they're staying the same. But they do look different. So carbon makes 4 bonds. It's part of its job. But if that gets arranged into this crystalline structure, it looks clear and is hard. It's diamond. And if it's arranged into these flat sheets, it's graphite, which is nice, but not the same as diamond. You see there? They still have to follow their chemical rules, but they do show up in a bunch of different flavors, if that makes sense. So far, so good? Also, they have emergent properties. So, I've asked about people who did Legos. Anybody here, like, a master maker? Nice. Anybody here, like, an okay maker? More hands, okay, thanks, sorry. Honestly, I feel like if you even can, like, do the box thing with the egg, you should count, like, I'm amazing. Okay. Remind me of your name?
Haley.
Sorry.
Haley.
Haley. Okay, so Haley, you're a baker. Did you ever tried either vanilla or cocoa plain? Has anybody here done that?
It's gross.
Yeah, it's gross. Was it super disappointing? Yeah, some people over here, like, hands over here, be like, I know better, because I have to cook it first, right? Okay. By itself, it's nasty, but it smells so good, and then you're very disappointed. If you ever try a spoonful of cocoa, oh, yeah, no. I don't recommend it. Okay. You've got these parts, these individual parts, vanilla, cocoa, sugar, flour, whatever. By themselves, they behave one way. When you put them together, what do you make? Anything, right? You can make cookies, you make brownies, you make muffins, you make bread, right? When they come together, there's something different than their individual chunks. Getting a muffin is very different than eating a raw egg, and then eating some flour, and then eating some sugar. Like, the experience is different. Okay? Right? Compounds have similar deal to that muffin thing. They're made of parts, but the compound behaves differently than either individual part. We're okay with that? So, sodium is downward. It is incredibly reactive. I'm posting these slides. This link, you can watch what happens if you throw sodium in water. Anybody know what happens? Yeah, thanks. Would you like to act out first? Right? Okay. It's kind of impressive. I'm not recommending it, but it's kind of cool. Super reactive. Chlorine is a gas, a poisonous gas, the kind of gas that the Geneva Convention says you shouldn't be using, right? Like, okay? It's a problem. Sodium chloride, which is sodium and chlorine stuck together, is table salt. Anybody put table salt on their food and have it go poof? No? See clouds of poisonous gas? Okay, for some of you it has. See clouds of poisonous gas coming off? Because of the salt? Okay, yeah, no. When you put together things behave differently, they've got emergent properties. Okay? The elemental identity is still the same, but they do different things. So far, so good? And then there's one additional level of complexity here, just to make things more complicated. We've got compounds. Compounds are beyond the sum of their parts, and compounds can behave differently as well. Or can have different identities. What compound am I trying to evoke over here? Water, yeah. So, water is water. Anybody, you don't have to, but you will by the end of this class. Does anybody know what the formula for water is? What's this compound?
H2O.
H2O, right? It's hydrogen and oxygen. It's H2O. It's a compound. It's a molecule. It's H2O when it's in clouds. It's H2O when it's in drinking water. And it's H2O when it's in an iceberg. Even though those are, like, there are some differences in clouds versus icebergs, if you're just looking at it. Okay? Cool here? But water still has its chemical properties of water. Okay, I think people are like, yeah, which is good. Any questions? Alright, we're going to talk more about this on Friday because I just feel strongly about beating this to death for you guys. More about the chemical context of stuff, but you can have atoms that are hanging out by themselves, you can have atoms stuck to each other and be like molecular oxygen, you can have two oxygens stuck together. You can have lots of atoms stuck together to other kinds of molecules. There's no actual size limit for this, you can keep sticking atoms together. You have atoms that are like close to each other. Oh, sorry, this we call molecules. You have atoms that are associated with each other but aren't intrinsically bound. We'll talk about this on Friday. And those are called ions. Sort of. Questions? Great. Alright. There are tons of elements. People in chemistry, do you know if Dr. Moore is making you memorize the whole periodic table? I don't know if she makes people memorize that or not. Anyways, there are a lot of elements. In biology, we don't care about all of them. Because, I mean, we do, sort of, but carbon, hydrogen, oxygen, and nitrogen make up about 95–96% of all life. We're talking mushrooms, and blue whales, and little protists, and you, those four, carbon, hydrogen, oxygen, nitrogen, they're most of what stuff's made out of. Like, a lot. Most of that remaining 4 or 5% are these few: calcium, phosphorus, potassium, and sulfur. Right? Doesn't mean these are the only important ones. There are a bunch of other things you need. You need iron, right? But you don't need that much. Okay? Iodine. There are a bunch of elements that are important for life and important for lots of different life forms. But these ones on the board are the big players. Okay? And I don't have a good way around this, but you've got to memorize the symbols for this set. Okay? So help me out here. The chemical symbol is going to be 1 or 2 letters that's going to indicate what element we're talking about. So you don't have to keep writing out carbon every time you want to draw a carbon. Okay? If you were going to come up with a 1-letter abbreviation for oxygen, what's the obvious answer? Oh, yeah. Okay, what about for carbon? C? Nice. You guys have this memorization thing nailed down. Hydrogen? Heck, nitrogen? You guys are like halfway there. Do know this list, by the way. Okay, so calcium, this is where we have our first problem. I want to C, but I can't see the carbon. Ca? We're cool with that? Okay, great. Phosphorus? We're okay with P? Okay. Here's the problem. Potassium. Phosphorus is holding P. Okay, you guys already know this. I was going to say, like, the obvious thing is PO, but it's K. Nicely done, class. Wow, okay. I did not know this until I showed up in, like, chemistry or something, and I was like, what the heck, people? And apparently, something to do with the Greek, something. The symbol for potassium is K. Alright? By the way, this is not the same thing as vitamin K. Common misconception, they're different things. Okay, sulfur, S. Okay, sodium is the one that is weird. Na. Okay, you guys know it's already. Chlorine? Okay, why am I even doing this stuff? Magnesium, Mg. For those of you who this is news to, memorize the list. For those of you who's like, I give you the chemical symbol of molybdenum. More power to you. Either way, know this. Questions about this? Stay tuned to this class for additional things that these molecules do, like farther in semester. Okay. Deep breath. Doing okay in time. Okay. So we've got this whole list there are a bunch more. This atom is the smallest unit that still has its own properties, its own elemental identity. And there are certain parts that determine how this thing is, what it behaves like. Your book and your homework go through this a lot. But briefly, and this is not to scale, I recognize it's not to scale. The basic parts are these. We've got atoms have this clump in the middle called the nucleus. It's got protons, they've got positive charges. Okay? Protons, the number of these protons determines what element it is. So if it's got 2 protons, the element's always, anything that's 2 protons, that's always the same element. Alright? Anything that has 48 protons is always the same element. Alright? In its sequence. Neutrons determine the isotope. We don't really care about this at this point in our lives. And then you've got electrons outside of the nucleus that exist. And I realize the model that you're shown is like the electrons buzz around like bees. They don't really do that. It's a probabilistic cloud, blah, blah, blah. Electrons are associated with the nucleus, but they're farther away. They're going to be outside it. Okay? These electrons are going to determine how reactive this stuff is. How much it goes boom if you throw it in water or other how many bonds is it gonna make? What's it gonna stick to? We're cool with this? Okay. With that in mind, that there are these parts that determine what this atom looks like, we are going to take a brief tour to Russia in the 1800s. Oh, it's over now. I should have. Come on. Remind me never to close anything on this computer, because it takes a long time to get back. Okay, so I have a story, and this is a true story, which makes me excited. There's this town called Polsk. I don't speak Russian, I don't know how to pronounce it actually. It's in the middle of nowhere, Russia. We'll zoom out here for a bit. Nope, middle of nowhere, Russia. Okay, finally seeing where we're at. Alright. Confidently middle of nowhere, Russia. Okay. In the 1800s, there's a family, fairly poor family. Both parents work at the local glass factory. They have, depending on which account you read, either 17 or 13 children. Either way, that's a lot. Anybody here have more than 12 siblings? Okay, cool. Like, I've got 4 siblings, and I thought we had a big family. But, yeah, okay, so, this kid born, he's the youngest. He's got like 16 older brothers and sisters, okay? And when he's like early elementary school age, his dad dies. Okay, so the setting we have here is mom with more than a dozen children, this kid who's the youngest of all these kids, middle of nowhere, Russia in the 1800s. How's life looking for this kid? Not so great, right? You're like, oh, okay, good luck being a peasant, kind of, right? Okay? So, when he's, like high schoolish age, most of his older brothers and sisters are out of the house by now, apparently. His mom's like, my kid is smart. Which, hopefully your parents think you're smart, right? I hope they do. You're like, yeah. But his mom's like, he's smart, and he's not going to grow up in the middle of nowhere, Russia, in a glass factory. He is going to do something with this talent that he has, okay? So he apparently like sells all their stuff, says bye to her other children, and gets on a horse with this kid, and just goes for it. They drove off to Moscow, which, like, it's kind of a trick. Especially as a poor horse that's like, what did I ever do to you, right? So they show up in Moscow, and mom's like, shows up to, like, the university thing there. And the mom says, basically, hey, my son is a genius, and you should let him in for free. And the university's like, no. And she's like, they tell you he's a genius? They're like, yeah, no. She's like, fine. We didn't want to come here anyways. We're going someplace better. So they get back on their poor, struggling horse. I actually don't know much about horse, but I feel like probably like at this point. And they head off to St. Petersburg, which it's not as far as middle of nowhere Russia, but it's not insignificant, right? So they show up at St. Petersburg. She shows up at like the Royal Institute of whatever, with her son's like, hey, my son is a genius. Also, you should let him in for free. And they're like, yeah, okay. And she's like, great. And then she probably dies. And the kid's there at the institute, and just briefly tell me the psychology. Does he feel any pressure to like study? Yeah, maybe a little bit. Okay. So he does great. He studies a bunch, and this guy is this is not him as like a 16-year-old. It took him a while for that impressive facial hair. Dmitry Mendeleev. Heard of him before? Yeah. Okay. So Mendeleev, he's there at this point. science is just figuring out about elements. They're figuring out that there are these chunks that like you can't break down chemical reactions any smaller. And they've got a laundry list of what they are. They don't have very many yet, but they have a laundry list of what they are. Mendeleev's genius is he writes that with index cards or little cards, they weren't called index cards at the time. Little cards, and he writes out basically how reactive are they, what are their properties, what do they do, how heavy they are. And he's got these index cards, and he realizes if he arranges them in an order that makes sense, in an order based on like weight, he can predict what things are going to do. So he doesn't have the whole list at this time, but he basically realizes, I can't remember which elements he deduces, but he basically realizes like, okay, I know sodium when it hits water boosts, right? And I know potassium when it hits water has very similar properties. So I bet there's an element that weighs as much as like RD thing, that weighs this much, and is going to have very similar properties to the other two, right? He predicts, so he arranges this. It's not the most intuitive order, just for the record. He arranges it on weight and other things. And he predicts the presence of a bunch of these other elements. And what's more is he's right. People find these elements and they behave the way he's claimed they're going to, without having seen this stuff, right? Because he knows what they're going to do, which is kind of cool, right? Anyway, so he does this, and the point of this is you can do it too, right? Like you can, if you know what the elements, how they behave in predictable ways. And because they behave in predictable ways, you can use them to understand what's going to happen. Does that make sense? So that whole point is it's important to understand chemistry. I'm going to stop the online video because the next bit is the seating chart. But if anybody, and you people too, if you've got problems with mastering biology, fitting the access code, email me or come talk to me afterwards. So I'm going to pause this and then stay put for just a minute.